I'm going to try to simplify, as if it ever could really be simplified, the idea of quantum mechanics, the understanding of the behavior of electrons. And why do we need to understand that? Because it's going to unlock for us how elements behave, why different elements combine and how they combine and form chemical bonds, and even what's kind of going on in chemical reactions down at the atomic and subatomic level. So we do need to at least scratch the surface a little bit about understanding where electrons are. So remember, protons, positive charge in the nucleus. Neutrons, no charge, also in the nucleus, acting as the glue holding all those positive protons together, because otherwise they'd all want to scatter, because likes repel against likes. And then you have the electrons that are orbiting around the outside in this big cloud. Most of every atom's volume is actually where the electrons are moving around. It's mostly empty space. Kind of scary thought. It's not our experience of solidity, of matter and stuff. So the real thing you need to understand from the basis is that all matter and all energy are kind of two different versions of the same thing. They're two different ways the universe, if you will, kind of shows itself to be or exists. And everything has characteristics of energy and matter, or particle behavior and wave-like behavior. As you increase the size of the matter, of the substance, the wave-like characteristics get so teeny, tiny, we can't perceive them. So it's as if they don't exist in our perception. We can't even design anything to really measure them directly. On the other hand, when we go down into these smaller and smaller and smaller levels of matter, when we get down to atomic and really subatomic size, like electrons, which remember are the tiny little lightweight parts of an atom, the line between particle behavior and wave behavior begins to become fuzzy. We know this with light, and that's actually where we're going to jump into the story. Okay, so electrons behave like waves as much as they behave like particles. Light and any other form of radiant energy, so when I mean light, I mean everything from gamma rays to X-rays to what we can see as light, to heat, which is infrared, all the way down through radio waves by which you get signals to your cell phone. That all of those things actually travel in discrete little packages called quanta. Oh, that's where the quantum mechanics comes from. In the beginning of this journey, historically, without me going into all the details and all the experiments, are Max Planck and Albert Einstein. Max Planck, at the end of the 19th century, in the late 1800s, was looking at how objects, bodies of matter, absorb and release energy. And it was believed that it should kind of happen like a ramp, continuously. If I add a little more energy, I'm going to get a little more energy out. If I add a little bit more, I get more out. Well, it turns out that it seemed like there were benchmarks. Put energy in, nothing happens until you hit a particular amount of energy, and then all of a sudden you get a certain amount out. Put in more energy, you have to go up to another point where now you get another specific amount of energy. The energy seemed to be quantized in set amounts. And that ultimately Maxwell Planck worked out an equation that correlated the wavelength, the frequency of waves, with the amount of energy in each wave. Einstein, one of the two things he won Nobel Prizes for, was his work with something called the Photoelectric Effect, where he took this information and looking at the behavior of certain metals, that if you hit them with light of a particular color, if it was of the lower energy, according to the calculations using Max Planck's equation, nothing happened. The metal didn't change in any way. There was no electric current that began to flow through the metal. But if I change the color of light, remember that color actually corresponds to a wavelength, a frequency, and therefore, according to Planck, a certain amount of energy. If I changed the color to one that was of a higher energy level, I got electrons coming off of that piece of metal. I got an electric current flowing. And if I turn the brightness of the light up, by the way, if it was lower energy, like red light is at the lowest end of what we can see, didn't matter how bright the light was, nothing happened. If I get to what's called threshold, a color of light, which is really a wave, a frequency of light, that has enough energy to kick an electron off of that particular metal's atoms, I get an electric current flowing. And the brighter the light, the more electrons flowing at that speed, whatever that velocity is that they're coming flying off the metal. If I increase the energy further, which means that I'm changing to a different, what we would perceive as a different color of light, closer to the other end of the rainbow. So purple is or violet is the visible part of the spectrum that has the shortest wavelength, the highest frequency. The electrons are coming off at a faster speed. But it happens in steps, quantum amounts, set amounts. The universe on the subatomic level is kind of digital. It's 1 or 0. It's this step or that step. Nothing in between. So, putting that together with the structure of the atom, and you may remember backstory that Ernest Rutherford and his students did work with shooting radioactive particles at gold foil, and they figured out that atoms are really mostly empty space but have a dense positive core. So the negative electrons that J.J. Thomson had discovered were parts of atoms must be somewhere on that outside, that empty space, moving around. But what keeps the negative electrons from falling into the positive nucleus, because opposites attract? Niels Bohr originally had the idea, let's treat it, they're particles, let's treat them like particles. Maybe it's like planets. What keeps the Earth from getting sucked into the gravitational pull of the sun? What keeps us from hurtling towards the sun in imminent death? You never thought about that before. Don't think about it too long, I don't want you to have nightmares. It doesn't happen, obviously. Why? Because the Earth has a particular momentum of its own, a particular inertia that wants it to go sailing off into space. That doesn't happen either. Instead, we're at a sweet spot of the amount of Earth wanting to fly in one direction and gravitational pull of the sun pulling us keeps us moving in an orbit. Niels Bohr said, maybe that's how electrons keep from falling in and releasing energy. They must have set orbits. And so he did all this math, worked it out with hydrogen. And where did he get his data from, or how did he observe? He looked at when we put energy into atoms, we can get energy back out. And the amount of energy that goes in, remember, set amounts, correspond to particular patterns of light, particular individual bands of color if we separate the light out using a prism or something called diffraction grating. And we can see only specific parts of the visible spectrum, only specific parts of the rainbow. And for hydrogen, there's a whole series of bands that we call its atomic emission spectrum. So if we have a gas tube, much like those halogen lamps that you may have seen, and we run electric current through it, so we get the atoms all excited, we put energy in, the energy gets absorbed, and in Bohr's picture, well, where's the energy go? It goes into the electrons. The electrons go from one orbital state to another orbital state. But because they're negative and the nucleus is positive, they're less stable. It's a less stable orbit. So the electron will want to get back down to its lowest, most stable energy state, the closest it can be to the nucleus without kind of falling in. And so to do that, it has to release the energy. Energy just doesn't appear or disappear. It goes somewhere. You put it into something, it goes there, and then if it comes out, it had to come out from somewhere. No magic here, maybe. So the energy out corresponds to a particular jump of an electron, a quantum leap. It's where they got the name for that TV show in the 1980s. So working off of this model, when atoms absorb energy, the electron changes its orbit, And then to release that energy, it has to change back to a lower energy state. And he mapped it all out for hydrogen, and it worked beautifully for hydrogen. And then when he tested his idea out using other elements and their emission spectra, it didn't work. Why didn't it work? Because electrons are not just particles. They're particles, but they think that they're waves. They behave like waves. And I don't want to go into too much of the detail of the work that was done. Let's just suffice it to say that, so at this level, we're at a state where the particle behavior, it's a thing, it's got to be somewhere, and it's wave-like behavior, it's moving. You know, a wave, you can never really pinpoint it because you can see it, but it's always changing its relative position, even a wave in the ocean. So remember, electrons behave both like a particle, which is what we always thought of it, and talk about it as, but as a wave. And so we can never really pinpoint exactly where it is. And we can never really say exactly how it's moving, because the more we know about one, the less we know about the other. The minute I say, there's an electron, it's over there. Furthermore, we're down to the level that's so small that electrons as particles and as energetic particles are on the same order of size as little bundles of light energy, or photons. So how do we see things? We shine the light on it, and then that light bounces off and comes to our eyes, or comes to a detector that we then gather information from. When we look for electrons, we actually crash into them and change what they're doing. It's called observer interference. Without melting your brain too much, this is where we get the idea that we kind of cause what we see when we get down to the quantum level. We only see the result of our observing. And beyond that, we don't really know. So, how do we describe this? Well, looking at patterns of behavior, looking at the atomic spectra, looking at this uncertainty principle that was proposed based on work from Heisenberg, all right, Heinrich Heisenberg. So the Heisenberg uncertainty principle. Another scientist by the name of Schrödinger said, let's look at it from a mathematical probability kind of way. And so he came up with this big equation, fancy calculus, to describe all of the aspects of an electron, to narrow it down to several different characteristics that we could then give a picture of, well, where is an electron with a given amount of energy behaving as a sort of standing wave? Think of like a guitar string vibrating. I can't really pinpoint where the string is at any one point while it's making sound, but I can kind of see the range that it's in. The probability of where an electron of a given amount of energy would be around its nucleus. And so Schrödinger was able to describe where electrons are in terms of an energy level. And within that energy level, there are different orbitals that aren't traditional go in the circle kind of around the middle orbitals, but areas where most likely this kind of electron would be found. Those pictures, I'm going to warn you, look a little weird. So, for any electron, there's its principal quantum number or its energy level. It's on the first energy level, the second energy level, third energy level, fourth energy level. Kind of the things that Bohr had described before he had to go back to the drawing board. But then, within each energy level, there are subdivisions, what we call orbitals. And so we can have an s orbital, which looks like a sphere. This is a representation of a three-dimensional graph. Maybe you've learned in math, you got the x-axis and you got the y-axis. Well, you may have also learned there's a z-axis. That's the third-dimensional part. And so if you take all the possible answers of where an electron with a particular amount of energy could be that fits what we describe as an s orbital electron, Well, it's going to be most likely 99% probability it'll be somewhere in that sphere moving around. Anywhere, and that's anywhere in the volume of that sphere. So not just at the edge. Anywhere from the very origin, which would be close to the nucleus, to some outer edge. There is a very slight chance that the electron we're talking about is on the other side of the moon. It's that weird. But most part, it's somewhere in there. If we go up an energy level from the first one only has an s orbital. When you go to the second energy level, now we have an s orbital, but we also have 3 different possibilities of things called p orbitals. And notice they lie around each of the axes. So there's one that lies around the x, one that is around the y, one that's around the z. And so it's not going in a circle around the nucleus, but it could be anywhere in this side, or from this side to that side. Don't think too hard about how that can happen. Just know that it is. Unless, of course, you want to explore this further because you're interested in becoming a quantum physicist. If so, have at it, get back to me, and teach me the details. Notice I only drew an s and a p. There are also d orbitals and f orbitals. And there's, on any energy level, there's an s. If there are p's, there are 3 possibilities. There are 5 possibilities for d's, and there are 7 possibilities for f's, and those look even weirder than the p's. And you can look them up. They're out there in Google Land. What you really need to have a picture of, and at the end of the day, what I want you to take home from this, is that as we go up in energy levels, there are sort of places to send an electron's mail, descriptions of where they could be in terms of their energy. So we can kind of simplify it down to just saying, okay, so if I have an electron and it's in its lowest possible energy state, if we're talking about hydrogen, the lowest possible energy state is the first energy level, and the only thing there is an s orbital. Every orbital can hold 2 electrons. Now remember, electrons are both negatively charged. They don't like each other because likes repel electrostatically. But electrons also have another property that's a magnetic property based on how they spin. They spin like tops. Some spin one way, so we say they're upspin, and the others spin the other way, so we say they're downspin. And that aspect of the 2 electrons in any suborbital are entangled in each other. If one is up, the other has to be down. They may be switching all the time until we observe them, and once we observe them, once we know one is up, the other one is down. And every observation that we've designed to do that has shown that to be true. It's the pattern of where the electrons are that we can then get our head around. Oh, so this is why lithium, sodium, and potassium are all in a family together. Because when we look at their distribution, even if we're not worried about what the pictures look like, but just in terms of energy, how many electrons do they have when we get to the last level that they're filled with, we're going to see a pattern. So we have a little map from all of this stuff. We have a little map that says, okay, each line can hold 2 electrons. First energy level, there's only an s. Second one, there's an s, and there's 3 p's. Third, there's an s, there's 3 p's, and then there's the d's, of which there are 5. Notice they go in increasing odd numbers. And if we went up further, past the 4 or into the 4, we'd also have a 4f. The one last thing to point out here, and there's going to be another video about how to do what's called electron configurations, defining the map for each element. When we get to the 4th energy level and we start talking about d orbitals, it gets even weirder than anything I've said so far. And what's weird about it is these degenerate or multiple equal options for d orbitals, when they're only partially filled, these electrons actually have more potential energy than the 4th energy level s electrons. A filled 4s is more stable than a partially filled 3d. So they actually overlap. And you say, well, so why is this part of the 3rd energy level if I don't fill it till after I start filling the 4th energy level? That has to do with the overall stability of the orbitals and the electrons. If every spot for a d orbital is filled, the differences between the s's, the p's, and the d's when they're all filled collapse. You can't distinguish them. Only when they're partially filled, and that's how these patterns kind of were worked out, is by looking at an element that only has 1 electron in a p, or 2 electrons in a p, and 3 electrons in a p. The distinctions disappear once the electrons, every possible orbital spot for that particular energy level is full. And then it almost begins to look, even though it's not really, but begins to look more like that simplified Bohr model of rings. It doesn't visually or physically actually look that way, but from our observations in terms of energy, they become indistinguishable. But when they're only partially filled, they look different. And so here's a pattern that we see actually play out in the way elements react, and how we can organize them based on that reactivity and increasing atomic number, increasing number of protons that we find in the periodic chart. So the organization of the periodic table actually is a supporting piece of evidence for this quantum theory. Okay, hopefully you're able to hang in for all of this, because this was a bit longer and a little bit confusing and complicated, and I stripped it down to its bare bones, trying to get to the point for you to understand that there's a pattern, that we've worked out the pattern, and once you learn that pattern, you can make sense of things like the periodic table, why certain atoms react with other atoms, and the kind of compounds they form. And some of this other interesting backstory may fade a little bit into the background, but I still think it's worth getting your head around just a little bit to understand when we talk about electron configurations. See you in that video.